Up to this point, we've been talking mostly about DC voltages and currents. So today we're going to take a look at AC voltages and currents, see how they're created in generators and some differences between them and DC. There are essentially two different types of generators, AC, alternating current, and DC, direct current. Inside the generator, deep inside in the windings that are rotating within the magnetic fields, the currents reversing flow. So all generators within the windings themselves are alternating currents. We'll see why that happens as we take a closer look inside. But their external design in the collection of the winding currents determines whether or not that the generator is classified as a DC or an AC generator. So when we talk about direct current, we're talking about directional current. The current flows in only one direction, as we're being shown in this circuit. And if you look at the current over a period of time, we see a graph here, the current's at a certain level, I don't know, 3 amps we'll say, and if you start the stopwatch at 0.0 here, then as time goes on, this current maintains a certain magnitude, but more importantly, it maintains a certain direction of flow. It never flows the opposite way. So pure or constant DC is an example of the previous slide. It maintains a certain level. Now as the battery would discharge, obviously you would see the level come down, but you would never see a reversal. You would never see anything in here indicating that the current was flowing in a different way. Now this is another example of DC current. And it's not steady, it's not constant. You see these pulsating, and it's called pulsating DC. These pulsating waveforms are being created by some circuitry or device, but even though it changes in magnitude, again, it's not changing direction, making it classified as DC. Here I have a DC voltage that's varying over time, and again, it's not changing direction, so it's DC. This is something you might see in a digital circuit. DC levels are often in these pulse wave forms, and in this case I have it's right here at this 0 point. I've got no current at all or no voltage. Obviously if the current is rising, if there's a change in current, it had to be caused by a change in voltage in these circuits. So here, this rise in current was caused by a corresponding rise in voltage. If this were voltage, it would look the same, and we would know that if the voltage was going up in the circuit, so was the current. But at this point, I've got no flow of current, no voltage, but at this instant, suddenly I'm turning on a switch, probably a transistor, that causes the voltage to rise to a level. In terms of voltage, this is typically 5 volts, and this represents digital data. This pulse, the length of time represents something, and the length of time in between the pulses represents something. Here the switch is open for a longer period of time, creates this longer, broader pulse. As opposed to AC waveforms where the current does change directions. Now there's a change in magnitude as well in this particular waveform, but more importantly what makes it an AC waveform is this departure from the positive realm into the negative. Because here we have a square wave similar to a pulse wave. It's changing direction rapidly. I've got a level, we'll say it's 5 volts again, and then suddenly at this instant it changes direction in flow and goes to an equal but opposite magnitude and another reversal, and this continues over time. A sawtooth wave where the voltage is ramping up and then suddenly discharging, ramping the other direction. You see how it gets its name. The generator principle apps, we talked about these last week. If you go to the PowerPoint slide, you should be able to click on these apps if you want to play with them yourself. We talked a little bit about different prime movers, what's turning the generator. In this case, the generator sits in this wind turbine. The prime mover are these blades driven by wind to rotate the shaft and also rotating the windings inside the electromagnetic fields of this generator. A diesel-powered generator. The diesel engine here, the generator here, controls cooling system, radiator, air intake. Here's a much larger generator. This is probably in a fossil fuel, coal or oil fired steam generator. Here's a bank of generators, maybe hydroelectric from a hydroelectric plant. All right, let's take a look at this. Here I have two generators on the top. One is AC and one is DC. How do I know? One, I can look at the waveform, alternating direction, and I see it also being indicated in the meter. Not only is it changing direction, but the magnitude is rising and falling. Here is a DC generator. Again, I have a winding that's rotating inside a magnetic field, just the same as over here, but in this case, I'm not reversing direction. I still have the rise and fall of the voltage. The voltage is rising and falling, but there's no change in direction. What's the difference? The difference is the external collection system, the commutators. In this particular design here, I have two rings. One ring is attached to one side of this winding, and the other ring is attached to the other side of the winding. And as the winding rotates, these brushes are collecting the current that's being caused by the induced voltage. Because this ring is attached to one side of the winding, that side of the winding half the time is going up, while the other half of the time it's going down. This side of the winding obviously is doing the opposite. So because of that, and by collecting the current in this way, we're able to capture that reversal in flow. However, over here, I have a different type of commutator. This is called a split ring. And in this particular case, I'm always collecting whatever side of the winding is going up. And the other one, I'm collecting on what's going down. So I'm always collecting positive on one side, negative on the other, and so I'm not seeing the reversal in current. This black separator splits the two electrical circuits, positive and negative, that allows that to happen. You know, whenever the black part cuts the brushes, whenever the black part crosses those brushes, these windings are in a point at 0 voltage. In this example, you can see the current changing directions as the winding rotates in a magnetic field. Now, Faraday's law of generation said that the output of a generator, e.g., E generated, is equal to the flux density and time. The flux density is the strength of the magnetic field. This magnetic field here. The more lines there are, the closer together they are, the more dense they are. So basically, the stronger your electromagnet is, or a permanent magnet for that matter, the stronger your magnetic field is, your lines of flux, the higher the voltage output. And T is time measured in seconds, and it's saying that we're talking about the time it takes to cut lines of flux. So the less time that it takes to cut a line of flux, then the higher the voltage. So as time goes down, the time in between cuts goes down, then this voltage will go up. So let's talk a little bit then of why the voltage rises and falls. We understand that it changes direction. We looked at some drawings that explain that. But how do we explain the rise and fall? Well, let's start by beginning with this winding. It's in a magnetic field. We have a black side and a red side to help keep us oriented. And this thing's rotating clockwise through the magnetic field. When it's at the top in a 0 degrees, it's not cutting any magnetic lines of flux because the winding is flowing parallel to the lines of flux. It's going in the same direction, so there's no cutting. Without cutting, there's no induction and there's no current. However, when this is rotated to the 90-degree point, now I'm cutting those lines of flux perpendicular and I'm at my peak. When I'm down at the bottom again, when the black is down at the bottom, again I'm running parallel, so there's no induced voltage because there's no lines of flux being cut. And then at 270, I've got maximum again, but in the other way. 360, back to 0, and it goes over and over and over as these cycles repeat. Let's maybe explain what's going on. The rise and fall have to do with changes somewhere. Now, is there a change in the flux density? Are these lines getting thicker? Are they more compact or dense in one part of this field than the other? And the answer is no. This is a uniform field. So as this rotates, nothing's changing here. Now, that brings in the speed of rotation. Because if I cut these lines of flux faster, that'll cause the voltage to go up. Well, it must be that, right? No, because think about it. This is a generator. It's sitting here rotating at a constant speed. It's not speeding up and slowing down, but my voltage is rising and falling. So, yeah, if it's not this, it has to be this. So how is the time changing? Let's see if we can explain it like this. Imagine two lines of flux, and let's imagine that you're the conductor and you're sitting and you're getting ready to cut a line of flux. Now I'm going to run 90 degrees perpendicular across that line of flux, and I'm running at a fixed speed. It takes me a certain time to go that distance, and that's the distance that I'm cutting the lines of flux perpendicular. At this point and at this point, I'm traveling in a straight line. But take another scenario where I'm going to go from one line to the other. The lines are still the same distance apart, and I'm still going to travel the same speed from one line to the other, but now I have to travel at an angle. It's going to take me more time to do that, and that's what happens here. As I'm cutting 90 degrees, I'm going from one line to the next in the shortest possible path, and so the least amount of time is taken and the voltage the highest. But as I travel around, now I'm traveling at an angle, and it takes me more time to cut a line of flux. So that's what causes the rise and fall in the voltage magnitudes. Kind of a layout of a practical AC generator. Here I have a DC supply that's creating the electromagnetic field poles. Notice that I have the same wire, the same conductor that's creating all these windings, and the current flows around this way for a north, but I'm going to wind this coil around the other way so the current flows the opposite direction around this pole to create the opposite polarity in magnetic field. Again, I reverse the winding to reverse the pole, and again. And my output is taken from these windings that are rotating and cutting the magnetic fields created by these poles. Let's talk about some terminology associated with waveforms. First thing is a cycle. A cycle is one complete wave of alternating current or voltage. So we have half of a cycle here and another half of a cycle here. And this is in the positive realm, so we call it the positive alternation. And then we call this the negative alternation. So to define where a cycle starts and begins, the definition is that a cycle is a point on this waveform from there until you get to the same point on the waveform, again, going the same direction. So let's start here. The same from the point till you get to the same point going the same direction. So I'm at this point and I'm going to go along this waveform and I'm at this point again. This isn't one cycle. It's only half a cycle. Why? Because yeah, it's the same point, 0, but I'm going up here and I'm going down here. So I'm going to continue around. Now I'm at the point again, 0. This time I am going the same direction. So from here to here is considered one cycle. I could have just as easily said from here to here or from here to here, but obviously if I'm crossing over an axis, it's easy to identify that point. The period is the time that it takes to produce one complete cycle. So the cycle begins, you start a stopwatch and you time it, and when it gets to the end, you stop the stopwatch and see how long that it took. And you measure this in seconds. The frequency is another aspect related to time, but here we're looking at how many cycles are produced in a second. So let's take a look at this. I have 1, 2, 3, 4 cycles in 1 second. That means 1 cycle per second is the same as 1 hertz. So 4 cycles per second, sometimes called CPS, but more often called hertz. 4 cycles per second is 4 hertz. We talked about inverse relationships when we were talking about resistance and conductance, light and dark, hot and cold. Frequency is the reciprocal of the period, so it just stands to reason that the period is the reciprocal of frequency. And it has to be that way, so let's think about that. In this case, I've got a frequency of 4 hertz. That means there's 4 of them in 1 second. If there's 4 of these cycles in 1 second, then how long must it take for 1 of them? Well, yeah, it has to be 1/4 of a second. So I've got 1/4 of a second here, 1/4 of a second here. This makes 3/4 of a second and a full second. Each cycle is 1/4 of a second, which is the reciprocal of 4 is 1/4. So if the period is 1/4 seconds, then the frequency is 4/1 hertz. The peak value, as kind of you can figure out, is the highest the waveform ever achieves. Positive and negative peaks. The peak-to-peak value, again as the name implies, is the peak to peak, and it's obviously going to be 2 times V peak. Now the effective value is the equivalent DC value of voltage. Because the voltage is rising and falling and the current's rising and falling, we can't really use peaks as a good way to solve problems with power. So this effective or RMS value is a better way to do that. And what we find is that the RMS value is here compared to the peak value, which is here. Let's take another example. Let's see why we're even doing this. Let's imagine that you have a room with a pile of sand in it. Now we can see what the peak value, the peak height of this sand, but what if I want to know over this the length of this room, what's the average height of sand for this room? Well, I'd have to kind of spread this out, right? Now imagine further that I have a hole in the floor. And now what's that going to do to the average? Well, as that sand falls down to that, my average height is going to drop. When I'm looking at an AC waveform, my pile of sand is exactly the same size and shape as my hole in the floor. So this fills this in, and the average over 1 cycle is 0. 0 volts, I have just as much positive as I have negative. Add those two together, divide it by 2, and I get 0. I have average current of 0, which means I have an average power of 0. So how do I ever get any work done in a circuit if my average power is 0? This is the problem with using averages from AC. Now, the reason that we get work done is, imagine somebody digging a ditch one way and now turning around and reversing the direction and digging a ditch the opposite way. Going the opposite way doesn't undo what was done. It continues to do the same work that was being done the first time. So whether current's flowing one way through a filament of a bulb or it's flowing the opposite way through the bulb, the same effect occurs and work's being done. Now, how do we calculate RMS values from peaks? Well, it gets complicated because you have to use trigonometry and calculus to get precise values. We're not going to do that. Instead, we're going to use another method. What I'm going to do is this. And we're going to simplify this. But let me just show you what they're doing and explain how it gets the name. What I need to do is get an average amount. We've got these peaks. How do we calculate the average? Well, we know we just can't add them together because that gives us 0, as we already saw. So here's the trick. What we do is we square this. We take this area here and we square it. So I take my peak, or my max, square it, and then I take this negative peak and I square it too. So this is the trick we use in statistics. If you want a negative number to count because it has some value to it, you square it. And now if you square a negative number, it becomes a positive. Now I can add two positive numbers together. This one squared and this negative one squared, two positive numbers divided by 2. And I will take now the square root of that to undo what I did with the square to give me volts RMS. I'm taking the root of the mean, the average here, of the squares. Root, mean, squares. Yeah, so it gets easier than this. Turns out, once you do all the calculus, and it only works with a sine wave, but if it's a sine wave, you can calculate the VRMS by taking the V peak and multiplying it by 0.707. 0.707. Why 0.707? Because when you take this waveform, use calculus and integrate, you can come up with this. So here's an example. I've got a current. It peaks at 10 amps. What's the RMS value using the formula we just looked at? 7.07 amps. Working back the other way, if I know what the RMS value is, how do I find the peaks? By the way, this is your house current. Your house current is 120 volts RMS, give or take. I've seen it run from 115, 125, and it changes different times of the day. But we'll just say 120 volts RMS. What about the peak? Well, I take the peak value because it's VRMS times 1.414, which is the reciprocal of the 0.707, which means multiplying VRMS by 1.414 is the same as dividing VRMS by the 0.707. So if you were to use the previous formula and rearrange it to make this work, that would be the same thing. All right, so we'll use this formula because that's what they gave us. And that's showing us the peak voltage is 170 volts. So that time when I was like 3 years old, nobody apparently was watching me, and I took a paper clip and stuck it into a receptacle to see what would happen. It said 120 volts, but what I was actually experiencing was 170 volts peak. Now V peak to peak is V peak times 2, so we're looking at 340 volts peak to peak in your wall outlets. You're only going to experience one peak at a time, but this peak hurts as much as this one. 1, 2, and 3-phase voltages. In our homes, single phase or one phase voltage is what we have. And if we see how that's produced, we see a generator here and it has a coil. Now, let's think about this a little bit. We talked about induction occurring whenever conductors cut lines of flux, or there's relative motion. In other words, if in this case the conductors are stationary, but the magnet's moving, so the lines of flux are moving and they're cutting the conductor. So there's still that relative cutting of flux, even though it's the magnet rotating in this case, where in the other generators we looked at, the magnets were stationary on the side in the field poles. Okay, so as this rotates around, we're going to get the sine wave, as we discussed when we were discussing sine wave generation before. In a two-phase system, which is pretty rare to see, you're going to have an additional coil, A coil and B coil. So A coil produces one waveform and the B coil's making another one that's 90 degrees apart because it's physically, mechanically situated 90 degrees apart from the A coil. And so electrically, the waveforms are 90 degrees apart. And in a three-phase generator, you have three coils. This is common for commercial and industrial applications. It's very efficient to transmit, and as you see, you're getting a nice supply, and during the time of one cycle, the one normal cycle of single phase, you're getting two more peaks of power delivered in that same time. You're getting 3 peaks of power instead of one in a single phase. It's smooth and it delivers more current over the same amount of time. Here we see some animations that show A poles, B poles, and C poles, the resultant waveforms. Here's another animation that shows the same thing. A separately excited generator. What's separate is the field. This only means that I'm going to generate voltage. My windings are rotating here, driven by a prime mover, diesel engine, wind turbine, whatever it's moving the coils, and this is my magnetic field. The magnetic field, we know that the output of the generator changes with changes in the magnetic field, flux density, Faraday's law. So if I can control the flux density, the strength of this electromagnet, I can control the output of my generator. And I'm going to control this strength of the magnetic field by controlling the current that's flowing through the field coils. So my current can leave here, and as I increase resistance, I will decrease current. A decrease in current will cause a decrease in magnetic field strength. A decrease in magnetic field strength will cause a decrease in generator output. This is what it might look like. Notice that I've got just one conductor for my fields. Turn one way for north, turn the opposite way for south. And I control the strength of the output by controlling the current in the fields. A shunt generator works off its own self. There's always a little bit of residual magnetism in the poles, in the field, to get this thing started. And as soon as it starts and starts to put out an output, some of it goes this way and self-excites itself. So we can control the output here the same way we did with a separately excited generator. It's just that this is self-excited. This shows how typically these leads are labeled in a schematic and in a terminal box. They put this picture in here of a backup unit. You may have one at your house. little Hondas, or maybe you have a natural gas or propane version, or maybe it's gasoline. So, use these for power outages. Obviously, hospitals need some sort of backup generation, and a lot of commercial and industrial applications, and now residential applications, have backup power. So they gave this as an example. This one's using a little diesel engine. Your transfer switch puts it online whenever the grid goes down. But I thought I'd find a more heavy duty version, and I found this. This is just the diesel engine that's turning the generator. This is just the prime mover. So the generator that's sitting over here has to be huge.